Hello, welcome guys to the climax of this module where we'll be looking at some applications of the Range-Kuta method. So, with Range-Kuta, we have got the second order Range-Kuta method, we have got the third order Range-Kuta method, we have got the fourth order Range-Kuta method, the sixth, and so on, or higher order Range-Kuta methods. So, I skipped the derivation of the method, but here it is. So for this method is closely related to this one where k1 is equals to f of xi plus yi, and then your k2 is f of xi plus h yi plus k1 h, where k1 is this one, and then your yi plus 1 is equals to yi plus h over 2 k1 plus k2. Alright, so let's look at an example how you apply these formulas. So if you're given a problem like this and you're asked to compute the next value or the value of x at 1.02 using RK2 Range-Kuta method of order 2, and then your differential equation is given by 1 plus x squared plus t cubed, and then x1 is equals to minus 4. This means that t0 is 1, h is 0.01. Right, so k1 using this formula, so f of x1 x plus yi, so this is k1 is h, so this one we've already multiplied by, you see this h here, we've already multiplied by the h there. Now example, so this will be h, f of x t 0 x minus 4, which is equals to, substitute by 1 and minus 4 here. For t, substitute by 1. For x, you substitute by minus 4. So if you do that, then you get 0.18. And then k2 will also make a modification, since on our example here we multiply by this h then, so we make a modification as well for k2. So it means that this h is already multiplied there, so it means that k1h is already there. So this means that our k2 will be h f of t0 plus h x naught plus k1. So k1, remember, you also multiplied by k h, so it's the same as k1h because the h you multiplied on the previous stage. So remember, t naught is 1, h is 0.01, so this one will be t will be equal to 1.01, and then for x, this y coordinate will be x naught plus k1. So x naught, remember, x naught is minus 4, then k1 is 0.18. So substituting those values there, h is 0.01, then f of this guy, so this is 1 plus x, remember x we say is minus 4, x naught minus 4 plus k1, which is minus 4 plus 0.18. So this should put minus 4 there, and then 0.18 plus t naught plus, remember this is coming from this t naught plus h, and h is 0.01, so t naught is also 1. So substitute this one by 1, and then cubed, and calculate that, you should get 0.1662. So this means that your next value, your y2 in this case, which is our next approximate value, is x1 plus 0.01. So in next stage is x plus 1.0 is given by yi, which is x1. Because we are started at x1, so this is x1 plus k1 plus k2 over 2, because in our case the h we already multiplied there. So it's x1 plus k1 plus k2 everything over 2. So this gives you minus 4, 0.18 plus 0.662 everything over 2, and this gives you the next value as minus 3.8269. Alright, so we have not reached our target. Well, our target is to estimate at 1.02, x 1.0. Now we are at 1.01. So we do this again, apply the formula again. So our x1 now, our k1 now is given by h f of, remember we are now on the next step, so this will be 1.0. So it's a t naught plus h, which is t1, which is 1.01, and then our x1 was computed in the previous slide, which is minus 3.8269, and then applying the f of x, substituting for those two values in f of x, you get 0.01 plus, for x1 substitute by this value, for t1 substitute by this value, should get 0.1669. For k2, you remember k2 is, we are evaluating f, but at which point? So at t1 plus h. So t1 is 0.01 plus h, which is 0.02. So you get 0.02 there. And then this one is x1, which is this one, the value computed on our previous slide, and k1 is this value there. So substituting, making relevant substitution, so this will be 0.01 plus 1 plus, we are substituting from f of x, so we are substituting from this, right? That's your f of x. So this is 1 plus your x squared, so your x squared is this guy, which is given by x1 plus k squared plus t, your t is given by this, which is x t1 plus 0.01 cubed, and this will give you 0.1546. This means that with k1 and k2 we can approximate the next value for x, which is will be at x 1.01 plus 0.01, our step size. So this will be x at 1.02. So x at 1.02 is equals to x on the previous x, which is yi, which is previous x, which is this previous x, plus half of k1 plus k2. So this is previously our x was minus 3.8269, this one, plus k1 1.668 plus k2 0.1546, everything divided by 2. So our value, x value at this point 1.02 is given by minus 3.6662. So that's how you compute your value at that point. Right, so and that's how you use the second order method, Range-Kutta method. So the third order Range-Kutta method has got 3k values. That's why I say RK3. It has k1 is equals to f of x as usual, and then k2 is f of x plus h over 2, and then yi plus half k1 h, then k3 is f of x xi plus h plus yi minus k1 h plus 2k2 h. So what you recognize here is you pass through this midpoint to this value. So like you are reducing the interval. So the higher you go in terms of this method, you are more like reducing the interval, and your predictor variable is the equation is given by yi plus 1, which is equals to yi plus h over 6 k1 plus 4 k2 plus k3. Alright, so the next method is the next formulas, the fourth order Range-Kutta method, which is also known as the RK4. So K1 is the same, f of xi, yi, and K2 is equals to f of xi plus h over 2 yi plus 1 over 2 k1h, and then k3 is given by xi plus h over 2 yi plus half k2h, and k4 is given by f of xi plus h yi plus k3h, and then your equation for predicting your y value is given by yi plus 1 is equals to yi plus h over 6 bracket k1 plus 2k2 plus 2k3 plus k4. Alright, so let's look at an example how we can apply this formula to solve DE using the RK4 method. So I want to use the RK4 method to solve this differential equation. dy dx is equals to 1 plus y plus x squared. So y is 0, y is 0. So it means that at x is equals to 0, y value is 0 0.5, and your step size is 0.2. So you want to compute y values. Start from 0, you want to compute 0.2 and 0.4. So that's your problem, and then you want to use these formulas. Alright, so let's apply those formulas for your first step. You need to identify your h you're given, which is 0.2. Your fx, y is given this 1 plus y plus x squared. Your x naught is 0, and your y naught is 0.5. So using the formula, the first one, this one, you can get your k1. So your k1 is f of x naught y naught, which is equals to 1 plus y naught plus x naught squared, which is equals to, substitute these values in that equation, you get 1.5. K2 will be f of x naught plus half h, comma, now not this, these are more like coordinate here. This is a coordinate. This is a coordinate. So it means that your x coordinate you are substituting by this, and your y coordinate you are substituting by y naught plus half k1h. So in this case, this is 1 plus, in place of y, you are substituting by this y coordinate now, which is this guy. If you evaluate it, you should be able to get y naught plus half k1, this one, and then h is 0.02. This should give you 0.15. And then this one, it's you are substituting for this x, you are substituting by this x coordinate, which is x naught plus a half of h, which is 0.2, which is 0.2 divided by 2 is 0.1 squared, which is equals to 1.64. And then your k3, which is f of x naught plus half h y naught plus half k2h. This is equals to 1 plus y. In place of y, we substitute by this formula, which is y naught half k2h. Remember, k2 you have this one, h you have 0.6. So if you say k2 plus times h, if you say k2 times h times 0.5, which is half, you should get 0.164. And then for this x coordinate, we substitute by this one, which is x naught plus a half of h, which is 0.1, which is equals to 1.654. And then for k4, it is f of x. This is f of x naught plus h for the x coordinate, plus y naught plus k3 h for the second coordinate, which is equals to 1 bracket y naught plus 0.16545. So this will be equal to k3, which is this one, times h, should give you 0.16545 plus x. So x, which is this x coordinate, 0. X naught plus x naught, which is 0 plus h. So h is 0.2. Then you square that because there is this squared. Then this will give you 1.7908. Now that you have computed K1, K2, K3, K4, you can then substitute in your formula, in this formula, so that you evaluate your y1. So y1 will be the same as y at 0.2. y1 is y at 0.02 because you add your step size. So this will be y naught plus h over 6 k1 plus 2k2 plus 2k3 plus k4. This should give you y naught. Remember, y naught is 0.5, and h you have k1, k2, k3, k4. So this one is just substitution. You should get 0.8293. So we have computed the value for y at 0.2. Then we'll continue the method using the formula so that we compute for y is equal y at 0.4. So again we compute for k1. Now k1, we have moved one step to our right. So our k1 will be equals to f of x1 y1, which is equals to x1 y1. Your x1, you have x1 is equals to 0.2. That's your x1. And then your y1 is 0. Because this is y at 0.2, so x is 0.2. And then your y is 0.893. So your x 0.2, y1 0.8293. So we substitute those two here, should get 1.7893. And then k2 is equals to f of x1 plus half h, comma y1 plus 2k1h. This should give you 1.9 1.981. So what you are simply doing, in place of this h, x, you substitute by this, the value that you will obtain. Then remember, x1 you know, x you know, so this is the x coordinate that you are going to substitute there. And then y1 you have, k1 you have, h you know, so this is your y value, your overall y value for this one, for this coordinate that you're going to substitute there. So if you add this, or if you compute this f of x here, you should get 1.9182. Same with k3. So for k3, you've got x1 plus half of h, which all these values you know, y1 plus half k2, k2 is this one, h is 0.2. Substitute x in place of x, you substitute by the value that you will obtain here. That's the one that you're going to put in place of h. In place of y, the value that you are going to obtain here, substitute for y then, and then your overall value will be 1.9311. Make sure you satisfy yourself that that's the value that you are going to get. And for k4, similarly, you do the same. So this will be x1 plus h. H is 0.2, so this will be x 0.2 plus 0.2, which is 0.4. And then this one will be y1 plus k3 h, and then you substitute the value that you obtain here for this h, then the value that you obtain from here for this y. So if you do that, you should get 0.2.0555. Now that you have got your k1, your k2, your k3, and your k4, you can substitute to obtain your y2, which is given by y1 plus your h 0.2 over 6, and then k1 plus 2k2 plus 2k3 plus k4. Your next value, which is y2, so your y value at 0.4 is 1.2141. Right, so from the results you can draw your summary table. So at point 0.x0 you had your y 0.5, which this was given information, and then at 0.2 you had your y as 0.8293, and then at 0.4 you had 1.2141 as your y value. So if you look at all these methods that we have learned so far, so the more or the higher order, the more accurate the method. For example, the Range-Kutta order 4 is more accurate than the RK3, the Range-Kutta order 3. The Range-Kutta order 3 is more accurate than the Range-Kutta 2, the RK2. And the RK2 is more accurate than the second order Taylor method. So these Range-Kuttas are more accurate, so like they have got minimum error, so we prefer them in solving most of these numerical methods. So in summary, the Range-Kutta method generates an accurate solution without the need to calculate higher order derivatives, and second order Range-Kutta method is a local truncation error of H3 and global truncation error at H2. The higher order RK Range-Kutta method has better local and global truncation error, and the function evaluated are needed in the nth order So RK method. So if you have got n functions, you need an nth order RK4. Thank you for attending or listening to this tutorial.